Yeah. All right, at the end of the day, last period, what did we do? We had a problem, right? And we didn't get a chance to go over. And so this will be, we'll do a couple of more static problems today, and we'll be done with statics, or we'll start new topics of work and energy on Friday. I have the homework due Wednesday, and work and energy, it usually isn't that hard, I don't think. But, you know, you might want to make sure you read the books started as soon as possible. So let's go ahead and cover the problem that we did before. So the previous problem, we had a wall, we had a tilted beam, and this beam had a mass of 100 kilograms, right?
Yep.
The center of mass would have been halfway along the beam. The beam had a length of 2 meters, right? Mm-hmm. And then this angle here with respect to the vertical was 20 degrees. And then I had a rope that was attached to this. Rope that was massless, and the height of this rope above the ground was 1.3 meters. Okay. So, and then and the rope was horizontal. Or it may not be in reality, but we'll assume it's horizontal, as I had it drawn. So, and we want to figure out what the tension in the rope is. So, how do you guys do that? What's that?
MG sign a theta off the bar, the center of my house.
MG sine of theta, okay.
That gives us the amount of full weight in the ball. Divide that by your 1.3 meters.
Okay, let's go see if we can get that. So we have the weight force going downwards, right? That's the direction of the weight force. It's acting on the center of mass. The R perpendicular, the distance from the rotation point to where that weight force is. I can just draw the weight force, you know, downwards, and I can just look where the radius intersects that. So that'd be this distance here, right? Would be R perpendicular, which would be the same as this distance here. Right? So we'll call this 20, this is 20 degrees. This is 1 meter from the suspension point to where the weight's applied. So 1 meter. And so what would R perpendicular be? How would you get that? Yeah, it'd be the sine of that 20, it'd be 1 meter, the sine of that 20 degrees, right? So R perpendicular is 1 meter sine of 20 degrees. That makes sense to everyone? So this distance here, this would be 70 degrees, right? You could have also said 1 meter cosine of 70 degrees. That would have worked just fine. Okay, same distance. Make sense? Okay, so this is our perpendicular, and then the force, the weight force, what's the magnitude of it? Be just 100 newtons, or 100 kilograms, times 9.8 meters per second squared, or, you know, just mg for hint. And therefore the torque due to the weight, what would that be?
1 meter sine of 20 times mg.
Yeah, that's right. 1 meter. It's it's R perpendicular. Weight equals the torque due to the weight. It's positive because it makes it want to rotate. Is it positive?
Yes.
It is, because it makes it want to rotate counterclockwise, right? So we'll call that a positive torque. So 1 meter sine of 20 degrees times mg. And if I plug in numbers, well, actually, I ended up with 335. 0.2 meters. Okay. Now that's the torque due to the weight. Now let's look at the torque due to the tension force. So torque due to tension force, this tension force is pulling this way, right? On there. So it makes it want to rotate clockwise. It'd be a negative torque. So torque, tension, is going to be the tension force, magnitude of the tension force, which is what we want, times R perpendicular. What's the perpendicular distance between the rotation point and the tension force?
1.3 meters.
Yeah, that's right. This, in our case, is R perpendicular, which is 1.3 meters. See, it's a little different than other problems because that R perpendicular changes to that vertical thing. But do you see why that'd be R perpendicular? Like, this is the suspension point, this is where the force is applied, this distance, same as this distance. Okay. All right, and there's a negative sign here. So if I were to sum up torque and set the result equal to 0, I would get 335.2 Newton meters minus tension force times 1.3 meters is equal to 0. If I bring this over to here, that's the same thing as just writing it like that. So I divide by 1.3 meters on both sides. That cancels out and I get the tension force. And that turned out to be 258, or 257.8. About 258. See what we did? So, we have, in the lab this next week, we have this apparatus here. So this is basically a boom, right? Yeah, there's a little pin that holds this into the hand, so you can take it out and weigh what this is. So this will be tomorrow. We're doing this. All right, so on this one, what we're going to do is the idea is to try and figure out what this spring force is, what force this spring exerts. So you're going to have to do some measurements on it. And, oops. And there's different, let me see if I can get this in. Yeah, so there's different places you can put this spring. Say it's here. So what I could do is I could measure the tension here and figure out, or the distance here, mass here, and try and figure out what this is. Now the best way to do this is to probably make it, you know, you'll have to measure the spring force for several different situations. Do you think you can do that? Like, say I have a mass here, and I have a mass here, and I have a mass here. Do you think you can figure out what the spring force is in each of these situations? And that's what we're going to end up doing. And so, just as an example, we've done this similarly before.
You need to know how long
Yep. Let's say I have a spring exert some tension force like here. This distance being, let's call this distance D. Okay? And let's say that this has a length L. The center of mass is L over 2, and it has a mass downwards M. Could we figure out this tension force here? This one's kind of tricky.
you know how much you're moving.
Let's say, oh, and we also know this distance. Let's say this is D2, so D1 and D2. D1's the distance on this way from the hinge to along the boom to where the spring's attached. D2 is the distance upwards here. Do you think we could figure this out? How do we do this?
I keep coming back to you have to know how far you stretch your spring.
Well, yes, we'll know the length. We know the length of this spring too. We can measure that. Maybe I'll call this L3, or L, little l. Okay.
You know how much will it take to stretch the spring out? Should be
Well, this one's going to be one where we're going to want to apply torques.
Yeah.
And we'll get the spring force, the tension force from summing up the torques. And setting the result to 0. This is actually one of the most awkward situations here where it's at an angle like that. I think we often want it to, we often want to pull it so that it's horizontal and add extra masses to it. That's a big chunk of the loud. But let's say that we're in this situation here. And we can try and figure out what this is, what the difficulty is. So this angle here, could we figure that out?
Yeah,
You need to know your
We have
three
a-
sides of your triangle, what are your
Yeah, this would be 90 minus that 10 degrees, right? And this would be 80 degrees here. This thing we don't know. This thing we don't know. Yeah, so this thing is very, very complicated, isn't it, right now?
Yeah, I can know what it was.
So if you want to figure out the spring force and the torque due to it, it's pretty tough. Yeah.
can you just cut that triangle in half to find the,
Like that.
I think the other way. Wait. Because wouldn't that give you a 90-degree angle against the side of the wall?
It sure looks like it might if you did it this way.
Yeah.
And but then this thing's kind of an awful shape to have to deal with. This thing left over here, right?
Well, couldn't you do it at the point of the, where the,
Like that?
where
Like
the,
cut it from where
where
the
the-
80 degrees is.
Like here?
No. Start where the spring touches and then go towards the wall.
Like this?
No,
Or
like
this?
that right there.
Oh.
And then you could find, that would be our perpendicular, right?
Yes, this is our perpendicular. Perfect. You're right. This is 80 degrees. We know this distance here is D2. Right? So that's what you do. You see that?
And
So
then
let's go ahead and do it. So let me draw this so it's a little bit neater. It's gotten kind of ugly. Okay, so I'm going to draw the beam like this, okay? You kind of narrow it so it looks like
Yeah, I'm gonna do this
Okay, and this I'll call angle theta. And this is 90 minus theta. Or we'll do 10 degrees. We'll keep it 10 degrees. That's 80 degrees here. Okay? So if you cut this triangle like this, and that's the proper construction, then this is a nice right triangle. This is 80 degrees. That means this is 10 degrees. And this is we measured that. That was D1. Okay. And we know then that the torque due to the spring will be whatever that spring tension force is.
times d cosine of 80.
Well, this will be the distance to the attachment point. This isn't perpendicular to the force, though. This would be what was perpendicular to the force, isn't it?
So then we have to do another one.
Yeah.
one.
Well, we're almost there.
So then it'd be,
So wouldn't you have two right?
wouldn't it still?
Couldn't you have two right triangles?
Yeah, we do have two right triangles now if I do that.
Yeah.
And you know.
And I know this thing. So this is D1. Oh, shoot, I should have drawn even a bigger picture, shouldn't I? All right, could have drawn a much bigger picture. Here's my D. Here's my spring. At an angle to the wall. Like this. This I'll call D1. From here to here. This distance here, this I'll call 80 degrees. This perpendicular distance here would be D1 sine of 80 degrees, right?
Mm-hmm.
This is
Wait, shouldn't it be?
the distance from the wall to where the spring's attached. Now the tension force goes like this, right? We want to figure out either the part of the tension force that's perpendicular to this D, or the part of the distance that's perpendicular to this. So I think
So then,
you could do something like this. So this is a right angle. This would still be 80 degrees because this line and this line are parallel.
so then it'd just be,
Well, doesn't that bisect a 90-degree
80.
angle though?
Oh yeah, well it doesn't bisect,
it'd be
maybe it does.
d1 sine of 80
Maybe
times
This is
sine of
getting
80.
complicated, isn't it?
Yeah.
Isn't it just d1 sine of 80 sine of 80 because you'll just have to do,
The other one's gotta be 80 degrees,
Which one?
the other angle.
This one?
That
On
one.
the bottom,
Yeah.
on the bottom right triangle you made, that's 10 degrees.
Yeah, so this is 10 degrees.
that
And that
one?
means, and this is a right triangle. This isn't a right triangle.
No. It's not.
Yes,
But
it
it's
is.
a right
The
angle.
other one.
This is
It's
the
not.
right angle.
Yeah, that
So it
should
should
be.
be 80 degrees,
Oh.
right?
This isn't the right angle.
No,
But if you,
it should be.
that angle is a right angle to your rod.
Yeah, it should be a real.
What's that?
The lines are parallel, they have.
Let's see, so this, let's see if we can figure out what the line is parallel. No, this is just perpendicular to this, I probably should have been more careful. This line isn't necessarily parallel to this.
Oh,
It's just perpendicular to this. Okay, as I have it drawn, it's kind of confusing.
Well, wouldn't it be easier if we had a right angle? Wouldn't it have a right angle? Like you're seeing a bigger triangle this way, wouldn't it?
Which one?
That, where the tension force is?
This thing?
Yeah.
And what right triangle?
Wouldn't you have a right triangle by the beam?
By the beam right here?
Not there.
No, that's not necessarily
Right here.
right triangle.
It wouldn't necessarily.
Yeah, this is not a right triangle here. Because this angle is, it's not known right now. Or you can measure that is.
We could, then Vino needs to do all that.
that's not what we're gonna do in lot, right? Ours.
So,
No, we're not doing this.
Okay, good. So we're basically just figuring out what function you do that's different, way different. Doesn't that mean there's 90 degrees?
yeah, this is
That's
90
gonna be our-
degrees here, this is 90 degrees here.
That's the tension.
So
This
this
is what
is
we just did
P1,
earlier, like earlier,
P1 sine of 80.
right here, kinda.
You can even measure this if you wanted to.
Wouldn't it be tangent?
Because the tension would be.
And then what? What was that?
The tension is in the spring, right?
Wouldn't it be?
This is a right angle, right? So this whole thing's a right angle. Right? Yes. So 90, you might, and we know, you know, if you know this distance here, and you know this distance here, you can definitely get this distance here, right?
Yeah.
And you can measure this distance here,
Mhm.
so we could definitely get this distance here, right?
You're measuring the length of the spring anyway.
So we could solve for that angle.
Yes.
Yeah, that one.
So if we know this distance here, and we, this is so messy.
If that's a right triangle, doesn't that have to be 45 degrees?
It doesn't have to be 45 degrees. The only thing about a right triangle is that this has to be 90 degrees.
Okay.
And you can construct all sorts of, you know, any combination of these. These angles have to add up to 90. They can be anything that would do that. All right, so let's say we call this length, let's call it A, okay? This length we know it's d1 sine of theta, 80 degrees. And you could measure that too. That means this angle, theta here, equals arc tangent of A over this d1 sine of 80 degrees, okay? Excuse me. Once I have this angle here, well, I could, and I know this R perpendicular, I could figure out, you know, you know, an angle that may be perpendicular to that. I could probably relate this angle to something that's perpendicular. Let me see if I can do this. So this goes straight up here. Yes.
Is, I don't know, how I worked it out is, okay, you're bisecting that one, so you got 45 degrees, 45 degrees.
But it doesn't have to be 45 degrees though.
It doesn't.
So this is 90 degrees, right? But that's all we know. We know this is D1 sine of 80. We could do something like this, where, let's see, this is 10 degrees, this is theta, this is unknown, that'd be the perpendicular to R. Wait, we just needed this distance here, right? And then we'll take the tension, set that equal to the torque.
Yeah.
Sorry, I didn't mean to confuse you guys. Does that make sense?
We're doing this tomorrow?
Yes, you are.
Really? I thought you just said we don't have to deal with that.
I think what I'm trying to get at
Yes.
is that you really want to have this horizontal and nice like this.
Oh,
okay.
So we don't have to deal with it.
We're not doing it at an angle.
What's that?
We're not doing it at an angle like that.
Yeah.
What you'll want to do is you want to add a mass, a known mass, until it's nice like this.
Oh.
But you could do it at an angle.
How do you
See
find that?
complicated
How
it
do you
is.
find our perpendicular?
Unless I find distances, I'll do it.
What was that? Sorry.
All you have to do is find our perpendicular, but there's no way to do that, is there?
Well, this, let's see, we know what this is, right?
Unless we find that angle.
We know what this is. This is also a right triangle. This is A. You can figure out, maybe even measure that angle or something.
Well, if,
You could
because
do
we've already got
We
this
just found
data,
theta,
we just
so
found,
we
if
can
we found
find
theta, then we can find it.
Yeah.
Yes, that's right. Once you find theta, you know this is D1 sine of theta, so it says
Cos.
Yeah, but we can't do that because the,
sine 80 degrees, say,
that's
sine of theta.
yeah. How do you find out what theta is?
And theta is arctangent to the angle D1.
Oh.
So this gets overwhelmingly complicated, doesn't it? Yeah.
Yeah.
So, yeah, it probably is ideal to maybe keep it at a horizontal arm. In this case, you add masses here until it becomes horizontal. I think that's a big part of it. If it's at an angle, there's a lot of work to be done. Oh, you're already done. Sorry, guys. Try and work through that, see if you can figure it out in a nice way. Sorry for the confusion, I didn't mean that to become that overwhelming. I thought it was really good. In this specific
What? You just could if you could talk.
Next time I won't do it.
Sorry to mess you guys up. You got thinking about it, right? Of course. Yeah. Well, what else?
On the one,
You like take the sum of the forces and the y and the force. So like in the x is and you would like mg minus.
Do you know angular?
But what else?
Here's the thing, so the acceleration here is A1, acceleration here.
Oh, yes, no, because that's.
Get a better look up here.
It's the friction and the.
If this angle's to remain the same, we need A2
Yeah, you have a drawer over
L2.
And so you just take, because the friction is mu s times L. That equals net friction. Take N.
What do you call it?
And then sum that in.
Yeah, similar.
So,
Okay.
No, I think it's because of this
like,
specific
you
one.
have the normal force of your cell for the normal
It
force
wasn't?
using the sum of
What?
forces in the y. Right. And then do the sum of forces in the x, and then static friction equals
Really?
mu s times the normal force. And so that would mu.
Maybe
Mu
it
is
is.
just like.
It's just a
coefficient. Yeah.
Yeah, so I didn't like that problem.
Because I keep setting it as the same as static friction. To me, it's saying static friction times normal force. Static friction.
But like, that's just those two together.
Well, check that. Because tomorrow, we have quiz on it. I don't really care if the last time they, I'm not worried about that.
I feel like.
I can find
I think in this specific one.
I understood and this particular.
Oh, so they didn't have, it must be 45, 45, 9, 45.
Yeah, I could.
45, 45.
See, that,
Yes.
this angle, I don't think.
Gotcha.
This angle is almost. Depends on
Over redox.
The numbers that it had.
Is there any equation?
You'll measure this.
Or is it just basically? where
Which
just
you're
have
trying
any
to
stuff
do
like
with charge.
And
then it doesn't have charge. Then, okay, so if it doesn't have a charge on the left and then it has a charge on the right, then that means it got oxidized. And it was oxidized by the acid. If it has a charge on the left and no charge on the right.
So it can you plus
You know this like
So the opposite.
when you have yeah, carbonate, CO2 plus rain, and salts.
Has no nitrogen.
No, because like,
Because in the book, they were all like super warm.
put that there, this one would be down here. Like this is weird triangle up here.
It would have nothing, right?
Yeah, that doesn't work awful.
so, but you do know that this is one side of
A sulfide
that would be the cotton
obviously carbonate salt, acid, yields CO2, H2O, and salt. And sulfite salt produces S sulfur dioxide, H2O, and salt. And ammonium and
once you have this, you
salt.
know that
That's rock hydroxide.
Every time.
You know what?
Because I don't know, I feel sad about that. Like every conversation, I'm like, yeah, I know. It makes me sad. That I
Basically
every day
everything.
I give me my next gift. Man,
Regardless is like this.
That's oxidized.
Really? Alright. I should just be single for the rest of my life.
Sand comes off. Free elements. It's
I'll tell you this, this is rough.
I don't know.
like free elements.
Oh my goodness.